My apologies. Yeah, that's working. Yeah, so I was saying that part of this larger collaboration, originally founded by George Lake, who recently passed away, but the work I'm going to present today is mainly led by Urmila and Michael and Arif, but there's collaborations and contributions from a large number of people that I want to acknowledge here. So let's talk about clusters and galaxy feedback. We've already heard the buzzline. Galaxy clusters are big. They're very useful for cosmology because you can see them from large distances. And Daisuke made a great case for the importance of galaxy clusters in his talk yesterday, particularly about how the baryonic content is easily observable in the X-rays and in the microwave. You don't have just these little lines of sight to measure the baryons. You can get the bulk view of what's going on with the baryons. And then in terms of galaxy feedback, here we have an opportunity to take the models that we use for feedback in galaxies and apply them to an entirely different scale to which they were not tuned in an effort to see whether we can actually, to use a phrase that Neil coined, holistically model both the galaxies and the clusters in which they live. And then finally, within when we're doing galaxy feedback, right, if I blow the disk out of the galaxy, who cares where it comes down, right? That's not my department. But in a cluster, we... Somebody got that joke. If you blow it out of the galaxy in a cluster, it does not escape the cluster. You still have the opportunity to see where that gas goes. That contributes to the contents of the cluster, and that produces additional constraints on your feedback models. Clusters, unfortunately, are hard. You need all these good feedback models to work well, which needs high resolution. Neil mentioned that the instabilities didn't make that much of a difference in the simulations, but they really made, they actually stalled cluster theory a decade ago because we realized these were problems. And so you need quite a good resolution in a large object, and you can do the math there for how many particles you need. And furthermore, you got to do all this in a single object, and so the load balancing on large machines becomes difficult. So it's a computational challenge. Nevertheless, we've done this suite of simulations that include a volume and a cluster, and a key ingredient in the simulations is the AGN feedback as originally implemented by Gillian Bellaveri and then improved on by Michael Tremmel. And as it says, we like our black holes to be certified organic, free range, and locally sourced. Now, as you might notice in Whole Foods, this means that they're kind of more expensive, but we think it's worth it. And just to explain what I mean, first of all, locally grown means that we don't place a black hole in the center of a virialized galaxy. We actually form the black hole based on local gas conditions, essentially trying to mock up a direct collapse scenario for the original black hole, so high density gas with low metallicity. So the free range means that the black holes are not tied to their galactic halos, as, for example, when galaxies merge, the black holes are free to do their merger on a separate time scale controlled by the dynamical friction within the halo. And then the certified organic, these outflows that you see here are an organic part of the simulation, right? We put in the AGN energy isotropically, And it's the morphology of the galaxy that turns this into the bipolar outflow that you see here. Okay, I made that point. So what does this buy us? Well, one interesting and non-obvious thing that the black holes have done for us, and this is work by Nicole Sanchez, which has just gotten accepted, so look for it. Nicole is the first author. That the AGN feedback seems to be responsible for getting the metals produced by star formation out into the CGM. And in this plot, she's showing the column density of oxygen-6 as a function of radius. Our simulations with black holes are shown in the solid lines. Without black holes are in the dashed lines, and COS observations are the points. And remarkably, we require the AGN feedback to get the metallicities of the CGM up into the range where it matches the COS observations. So that's a non-obvious result. And furthermore, if we're going to actually make predictions for future observations, and this is work by Irina. If you haven't seen her poster outside, do go and see it. Where she takes here, on the top, we have the physical characteristics of our cluster. It's a 10 to the 14 solar mass cluster. Irina has projected that into observational space, X-rays, the O6 column density, and the neutral hydrogen column density to make predictions for, well, hopefully future HST observations. And again, this is requiring the AGNs to get the metals out into the, in this case, the CGM, so that we can, so that it can be observed. So those are the observables. I want to talk about quenching and feedback in this cluster. But before I do, I just want to point out that the cluster indicated by the round points does reasonably fit on these scaling relations, in this case, central entropy and bulk entropy of the cluster as a function of cluster temperature. Here we have some Chandra clusters in the black, and we see we fall in the scaling relations. This by itself shouldn't excite you, but what it does let you know is maybe it's worth looking at this cluster to examine the dynamics in this particular case of galaxy quenching. So the galaxy, here's looking at the brightest cluster galaxy at the center of the cluster. Is it reasonable? Well, it does fall on the stellar mass, halo mass relationship derived by abundance matching, a little bit high, but not too bad compared to, again, the abundance matching results. The morphology, well, I'd like it to look like an elliptical. It's certainly red and dead, so these are the standard UVI color. So, no ongoing star formation, but it's more of an S0 than elliptical, and you can see it's quite disturbed, and you'll find out why in a second. The star formation, as well as the star formation, there's an AGN going on in the center of that thing. And you've seen this outflow picture before. Here it is in density. You can see that the gas density is what's constraining the flow to go out in this bipolar fashion. The fact that it's being blown to one side is actually, the ICM is actually sweeping the jets to one side. So there's a lot of motion in the ICM. These winds, they go on throughout time. So these are various snapshots of that central galaxy across cosmic time. And you see the winds, those winds keep going throughout time. So what are the winds doing to the star formation? So here I have a plot, again, over cosmic time. out to in gigayears. And in the red is the energy injection from the black hole, the AGN energy injection. You see that there's these spikes, and in the blue is the specific star formation rate. And you see it very interesting that in the early universe, a spike in AGN activity means a decrease, so there's an anti-correlation with specific star formation rate. As we get further on, the correlations are not so obvious. One interesting thing is there's this ongoing AGN activity with this secular decline in star formation activity. But at the very end, there's a complete lack of star formation in the very middle, and it's not clearly correlated with the AGN activity. And in fact, we see that at the very end, both AGN and star formation seem to be gone. And what is happening here is that there's a major merger coming in that is strongly affecting the intercluster medium. So we'll talk a little bit more about that. Let's blow up those last few gigayears and take a look at here now I want to look at what the AGN activity is doing to the ICM. All right, so we have the AGN activity in blue. You see all these spikes. To measure what's going on with the ICM, I'm looking at the entropy, or the pseudo-entropy, basically temperature divided by electron density to the 2/3. And you see that nothing is being done to the gas entropy, at least on average, by the AGN. And this strong increase in entropy at the very end of the simulation seems to be anti-correlated with the AGN activity. So there's something else that's strongly increasing the entropy of this cluster core. And by the way, right, to get the terminology here, there's two kinds of clusters in this world. So the clusters where the temperature decreases towards the center, we call cool core clusters, or if you're really old, you call them cooling core clusters. And then there's the non-cool clusters where the entropy is flat in the middle, corresponding to a rising temperature as you go towards the cluster center. So we have this transition from a cool core cluster to a non-cool cluster, and it appears that actually AGN has nothing to do with it. So that's interesting. And so let's take a look at these cluster phases. So I'm going to pick 4 snapshots, one with low AGN activity, one with high AGN activity, one right before the merger, and one after the merger. You can see what things look like here. You can see the low entropy core, independent of whether the AGN is non-active or active, and it's during the merger that core goes away. Notice that the density doesn't seem to change that much, slight decrease in the core density. Here's the guy that's about to merge, okay? That's an incoming large galaxy. In profile, here you see the flat entropy core. So this is entropy as a function of cluster radius in spherical shells. You see in the temperature, there's this, right, the AGN going from dark blue to blue, you see that it's increasing the temperature, but it's not bringing it up to this increasing profile that we get after the merger occurs. And again, a little more detail of what's going on with the entropy. Here I'm doing a mass-weighted plot of entropy versus radius, so a 2D histogram. So early on, you see that in the center, yes, there's some high entropy stuff, but there's also a lot of low entropy stuff in the middle of the cluster. These streaks out here are other galaxies coming in. Thank you. And then by the end, this low entropy stuff in the middle of the cluster all goes away. Also, I have plotted on here in red are particles which have received AGN feedback since 6 gigayears into the simulation. So relatively recent AGN feedback. So you see that these particles get feedback, but what happens to them is they just float up out of the cluster center, leaving behind other cool gas, not increasing the entropy in the cluster core. That appears to be coming from the merger. And just looking at morphologically, these are plots of the entropy distribution in the central 100 kiloparsecs. Here you see a disk before the merger, and essentially, all right, the center of the cluster really is right there, but you can't tell where it is from the entropy plot because it's a flat entropy distribution. So questions about exactly the details of how cooling is being suppressed. We're still looking into it, but one thing we looked at is this ratio of the cooling time to the freefall time that Mark Voigt proposes as a measure of when precipitation begins, right? Precipitation should happen when it gets about at this level, and we see that after the merger in a non-cool core state, this cooling time is uniformly large across the cluster core. Like I say, the BCG just does get quenched, but here it is in 3 projections. I wouldn't call that an elliptical, but this is what it is before. You can see that it was star forming up until about a Z of 0.4. It does become completely quenched, but not a pretty elliptical. I want to just point out that we're not totally surprised by this result because of work that Andrew Ponson and Mike Tremmel did a couple years back, where they pointed out that the size of a merger makes a big difference in quenching a Milky Way-sized galaxy. Although in these plots, right, the AGN is needed, and so in the large merger, you still have AGN activity, but notice that, and it's hard to see here, notice you can't see from the back, but this is circulating like a disk here, and this isn't. And so there's more of a disk in the suppressed merger, and so the AGN feedback is more isotropically distributed, but it's not like Eddington, right? The AGN, yes, is going, but it's not particularly powerful at that point. So this is still preliminary work, still trying to understand what's going on, but here's a few points that I want to emphasize. Right, I downplayed this, but this is kind of important. We do have this simulation where we somewhat believe the results in that we can reproduce observed cluster properties. This is a big step. So answering your question, do you need AGN or mergers to quench galaxies? And the answer to that question is yes. The effect of the AGN seems to be to keep the cluster sufficiently soft, and well, this is my idea, sufficiently soft, that when you have a merger, it can drive the entropy up to this non-cool core state. Looking forward, right, clusters are expensive, and so I've only simulated a few and only really analyzed this one. I've got a few more. Simulating a population of clusters would be crazy expensive. This will be an exascale project, but I think it can be done, but we've still got to wait a few years. I should point out that even at the resolution that we use for this cluster, I'm not completely satisfied with. I prefer to go down at least an order of magnitude more in mass so that you more reasonably resolve molecular clouds. And so I'm going to push this genetic modification technique where we can get statistics, basically changing the nature of mergers and knowing the statistical significance of your change with this technique that Andrew Ponson pioneered, and I'm looking forward to work by Ben Keller and Michael Tremmel, who's going to go to work on this for massive galaxies. So I want to end by thanking the people that, the resources made it possible. Particularly, I spent a lot of CPU hours on this facility to run that cluster, and I also want to thank you folks for listening.
Okay, way in the back. Oh, Joe.
Yes, can you comment on why you think the merger is red herring in terms of increasing the entropy and perhaps the state integrated activity of the black hole that has
Well, all right, so I did point out, yeah, so you're going back to, I mean, if you look at this plot, there's not much, right? So there's, what's the difference between this and that, right? And, it's not that significantly different. And, just looking at the details, it seems to be that the effect of the AGN is that you raise a subset of the gas to high entropy, but as soon as you do, it floats away, and then there's more low entropy material just flows right in. So, because even when we put in the AGN as isotropic, right? So basically the substructure in the gas, in this particular case a disk, you can't get rid of that disk just with AGN feedback.
The question is it a fluke? I mean, can you do some kind of merger? I mean, there must have been much of other mergers earlier on that clearly didn't do this. I mean, I can't believe that was the only merger that took place with the BCG in the entire history of the BCG. But looking at other clusters, do you have any feeling for, how common this would be? Maybe other ones would happen even earlier on, or maybe this is like a fluke and most won't have this. I mean, you have to look at
No. I mean, that was sort of, my last point there. I haven't really done that. I mean, this merger is really a head-on merger. And so, and that might be a problem, actually. Maybe those kinds of mergers just aren't prevalent enough to explain elliptical populations. So that is a real worry. But future work.
We can do one more question while Mara was getting set up. David? David?
Noticed in your images of the BCG and redshift 0.5 look like a very nice spiral galaxy. And I was curious whether the other galaxies also look from the late type rather than early type, which is what we would expect from the generation 0.5 clusters back then. Large fraction before we were just searching for early type S0.
Yeah, so to be honest, we have difficulties making ellipticals. Yeah. 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 Yeah.
Okay, let's thank Tom again.